Hey everyone, Ryzen here. Understanding Bitcoin's proof-of-work consensus mechanism is crucial for anyone diving into blockchain technology. In this video, we'll explore a TypeScript implementation that demystifies the core components of Bitcoin's mining process. We'll walk through code that handles block header construction, hash calculations, and the mining process itself, all compatible with the actual Bitcoin protocol. By breaking down this concept into readable TypeScript code, we'll gain practical insights into how Bitcoin's proof of work actually works under the hood. You can find the full code on GitHub. To make our exploration more practical and grounded in reality, we'll work with actual Bitcoin blockchain data. We'll use the Blockstream API to fetch a real Bitcoin block, allowing us to verify our implementation against genuine blockchain data and demonstrate how mining works in practice. We'll make HTTP requests using a helper function called queryURL that handles the API calls and response parsing. Before we do the mining, let's verify that we can properly compute the block hash from the block data. A block hash in Bitcoin is calculated by hashing the block header, which is an 80-byte structure containing 6 essential fields. These fields each serve a specific purpose. The version field tracks protocol upgrades, the previous block hash field links blocks into a chain, the Merkle root provides a compact representation of all transactions in the block, explained in detail in the corresponding YouTube video in the description. The timestamp ensures chronological order, the bits field encode the current mining difficulty target, and the nonce is a variable that miners modify to find a valid hash. Our getBlockHash function handles the process of packing these fields into the header structure, ensuring proper byte ordering and field sizes. By comparing our computed hash with the actual block hash from the blockchain, we can verify that our implementation correctly follows Bitcoin's protocol specifications. Together, these fields ensure the integrity, ordering, and immutability of the blockchain while enabling the proof-of-work consensus mechanism. Bitcoin uses a specific hashing algorithm that applies SHA-256 twice to the input data and returns the result in reversed byte order. Now let's look at the core mining function that implements the proof-of-work algorithm. This function takes a block template without a nonce and a starting nonce value, then incrementally tries different nonces until it finds one that produces a hash meeting the required difficulty target. This process is computationally intensive and at the heart of Bitcoin's security model. Miners must expend real computational work to find a valid solution, but verifying that solution is trivial for other nodes in the network. In our demonstration, we start mining from the block's nonce -20 to quickly find a solution, since the actual nonce for this block is a really big number. In reality, miners have to test billions of nonces before finding a valid one. What's fascinating is that despite the immense computational effort required to find a valid nonce, verifying the solution is lightning fast. Just 2 SHA-256 operations. This asymmetry between the difficulty of finding a solution and the ease of verifying it is what makes Bitcoin's proof of work both secure and practical. The final piece of our mining implementation is the difficulty check. Bitcoin uses a compact format called bits to represent the difficulty target. This is a 256-bit number that a block's hash must be less than or equal to for the block to be valid. The bits field uses a floating point-like format with an exponent and a coefficient to encode this target threshold efficiently. Our check difficulty function decodes this format and performs a comparison, implementing the same validation that Bitcoin nodes use to verify blocks. Through this implementation, we've broken down Bitcoin's proof of work into its essential components: block header construction, double SH256 hashing, difficulty adjustment, and the mining process itself. While our TypeScript code is simplified compared to Bitcoin's core implementation, it demonstrates the core principle that secure billions of dollars worth of transactions on the Bitcoin network. If you enjoyed this content, please remember to like this video and subscribe to the channel.